Okay, we're going to go to section 7.4, separation of variables. And this is our second way to solve a differential equation. Did I actually hit record?
Probably not. Is the green light flashing?
I did. The
Red
red light
flashes.
is flashing. So, our goal is to solve a differential equation using separation of variables. Again, this is very limited. Just like what we learned last time was super limited, we could only work with stuff that was easily integrated. So stuff that only had x's on the right and the derivative on the left. So we had derivative, dy dx, derivative on the left. Everything on the right consisted of only x's. That's so far all we can solve. Basically, normal integration. It's just asking you to integrate. Separation of variables will apply to a new situation. And we're going to have both x's and y's together on the right side, but they have to be in a certain setup so that we can do some separation. And we'll see the setup in a second.
So far. Yeah. It's like 2 inches off. Yep, sure. Good. It's better.
So last time, if I gave you something like this, dy dx equals x plus 1, what would we do with that?
Plug in X.
Because they're always going to ask us to solve the differential equation to find the general solution. How do I find the general solution for this?
Take the integral.
Take the integral.
No, at first.
So we didn't have to do anything before we took the integral. We just took the integral.
That's the easy.
This.
Let me get this homework. 10x tangent 16.
So the difference between what we did last time and what we're going to do this time is now we have x's and y's together on the right side instead of only x's. I cannot integrate when I have x's and y's together unless I am doing multivariate calculus, which we are not doing. So I can't just go straight to my integrate part. But because this consists of divide, or if it consisted of multiply, I can rearrange stuff in such a way that I could integrate. So the way we know something is separation of variables is if it has x's and y's together on the right side, and we could move stuff around with multiplication or division. That's the only type. If that was 2x plus y, we'd throw up our hands and burn our books because we don't know how to do it. So, I want to get all my y's on the left side, all my x's on the right. I want y's only equal to x's only. Including my dy and my dx, I also want those as part of the y's only, x's only. So what do I need to move? Okay. Dx needs to move because right now it's on the y's only side, and we want it on the x's only side. So we multiply by dx. So that was one of them, and then I think you said the other one first.
The other way.
The y. The y also has to move because right now it's on the x's only side. I want it on the y only side. So I need to multiply by y. So we would get y dy equals 2x dx. So now if I have only y's together and only x's together, I can integrate both sides. So it's similar to what we did last time, except we have the one extra step of getting all the y's on one side, getting all the x's on the other side. And now I can just integrate. And when I integrate y dy, I do have to integrate that like I would an x normally. So what would the integral of y dy be if we're treating it as we would normally an x? 1/2 y squared. Now, we could write plus c, and we should at some point, but so I'm going to write some work to the side just so you can see what would happen. If I add a constant on the left, and then I go and integrate my other side and add a constant on the right, and I combine my constants, what's a constant minus a constant?
A constant.
A constant. So we usually do not write the constant on the left. We just skip to writing plus c at the very end, because that way we don't have to write c1 and c2 and subtract and combine. It's just always going to come out as plus c on the right, so we might as well skip to plus c on the right. We integrate the other side, x squared plus c. Now, they'll write the answer in two different ways on the AP test, and you won't get full points unless you write it the correct way. So, most of the time, they'll want you to get y by itself. So on this one, how would I get y alone?
Multiply by 2.
Multiply by 2. And then square root both sides. So we would get y equals square root of 2x squared plus c. So sometimes they will want you to write your answer that way. As you can see, it gets a little bit messy as we're going along. Usually when we do these, we're doing it with exponential functions, but we're not going to practice that as much today. I'm going to save that for next time. And they'll want it to say y equals. The second way you might have to write it is to actually get c alone. If we go back to the 1/2 y squared equals x squared plus c, quite often they get c alone to write the final solution. On the homework, let me check and see which way they're writing it in the book. They are getting y alone in the book. So for the homework, you are going to get y alone. So I want you guys to try a problem. Does everyone have this down before I
Nope.
go to the next page? Okay.
Clean.
So try this problem. So when we do this, we can only move stuff with multiplication or division. And if I can't use multiplication or division to move it, I can't solve it with our current level of knowledge. So the most common thing I'm seeing, most of you guys got to negative y to the negative 1 equals 1/2 x squared plus c. And then we could move the negative over, y to the negative 1 equals negative 1/2 x squared plus c. So if we have really 1 over y equals negative 1/2 x squared plus c, and we want y alone in the numerator, we're going to have to times both sides by y. Yep, or if you remember switchy witchy, then we would get 1 equals all of this, and then we divide by all of that. So we would have 1 over negative 1/2 x squared plus c. Now, most of the time when you're doing a differential equation, they don't want the c, they don't want the constant. They want to give you an initial condition so you can find c. Now, when we plug in our initial condition, it's actually best to plug it in right after you integrate. That way you don't make any algebra mistakes as you're rewriting everything. And then when you plug in your initial conditions, if you have an algebra mistake, it's going to make C incorrect. So if we want to find C, everywhere I see Y, I replace it with with 1. Just happened to be negative because it was negative Y. Where I see X, I replace X with 2. And then we simplify. We have negative 1 on the left, positive 2. 2 squared is 4, divided by 2 is 2. And we get C is negative 3. Okay. And you plug it back in also in the same spot up here. So we get negative y to the negative 1 equals negative 1/2, nope, positive 1/2, sorry. X squared minus 3. And then you would go through all the algebra. So on most of them, we're actually going to do and find C first, and then go do the algebra to get y alone. So we're going to find C first, then get our final answer by isolating y. So these are the easiest versions where it's easy to see what I can add and what I can multiply. There are some more difficult versions. On first glance, this looks like one we wouldn't be able to solve. Mostly because we see a plus sign there and we think, oh, we're done. Can't solve this. But they like using some algebra tricks. A lot of the AP tests do miss because they like using all these algebra tricks. Okay. So if I have e to the y plus cosine x, I can rewrite that to be a multiply problem. How can I rewrite that?
E to the y times e to the cosine x.
Exactly. This whole thing can change to be e to the y times e to the cosine x. We usually, again, are used to seeing it when we're multiplying. Hey, I know to add my exponents. We don't see it as often when I'm adding my exponents. I can switch it back to a multiply problem. And they love using this trick on the AP test. They love having exponents adding, which means you're really multiplying. What if it was a minus sign instead? Divide. I could have e to the y divided by e to the cosine x. So once we do that step, now it's all back to normal business. We just want to get all the dy's, or all the y's on the left, including dy, all the x's on the right, including dx. So we know dx has to multiply over. What on the right side is going to have to move? E to the y. And how am I going to move it? Divide it. I'm going to divide both sides by e to the y. So we get 1 over e to the y dy equals sine x e to the cosine x dx. Now I do have to rewrite this left side as e to the negative y dy before I can integrate. So now with these ones where it is a little bit trickier, we are going to have to use more advanced integration techniques. Instead of just anti-power rules or things like that, we need to use some other integration techniques. On the first one, yes, we know the integral of e to the y is e to the y, but the integral of e to the negative y, I've got to use u substitution because it has that negative value. So we know u would be negative y, which means dy would equal du over the derivative of negative y, or negative 1. So we would get the integral of e to the u times du over negative 1. Now on the right side, what are your guesses for how we should integrate the right side? So we're thinking u and dv. But what's going to happen when we try and integrate this as dv? So we have to do u sub again. Anytime we have an exponential function and we're doing u sub, u is usually the exponent. So then we would get dx is du over negative sine x. So again, we have to go and do our replacing. We have the integral of sine x e to the u times du over negative sine x. Sorry, sine x is canceled, but we will still have that negative out front. And I guess maybe we shouldn't have used u twice since we're doing two different variables, but as long as you can follow along which one goes with which, that's fine. So now we integrate, and in both cases we're basically integrating the same thing. One started out as y, one started out as x. What's the integral of e to the u? E to the u. So we get negative e to the u, because it was du over a constant, equals negative e to the u plus c. And we have to replace back in. What did we say what did we say u equaled when we were working with our y values? Negative y. And then on the right side, what did we say u equaled when we were working with our x's? Cosine x. So now, if we were going to find c, we would need some more information. I would have to give you some initial conditions. So for x equal to 0 and y equal to 0. So find c. plug in those values and find C. So you do have to be careful. A lot of you guys said cosine 0 is 0 instead of 1. We do really need to have those trig values memorized so we don't make little tiny mistakes like that. Sorry. So if we plug stuff in, we plug in 0, we plug in 0, then we would get -1 equals negative e to the 1 plus c. So c is e minus 1, or -1 plus e, either way you want to write it. So we can plug that back in for c, and then we still need to get y alone. This one is also tricky with the algebra. So first, let's get the negative, why did I write just c, plus e minus 1. Sorry. Let's get rid of the negative in front of the e. So how can we get rid of the negative in front of the e? Divide everything by -1. And the reason we want to do that is because as soon as we have e completely alone, what can I do to get rid of e? How do we get rid of e when we're working with equations? Natural log. We always do opposite operations. When we're working with equations, opposite of e is ln. So we ln both sides. So we would get -y equals ln of e to the cosine x minus e plus 1. And now we just have one more thing we need to do. Get rid of the negative. So we really just have positive y equals negative ln e to the cosine x minus e plus 1. So some of the algebra on these is a little bit trickier. So do you want to do one more try problem, or do you want to get started on the homework and I'll just walk around and help you on the homework? No opinion?
Homework.
Okay, Ben made an opinion. No one else did. Ben wins. So your homework. The wrong month. December. Page 361. 1 through 10, all. And we definitely have enough time today for a phone hour assignment. You may even finish. Have about half an hour, so.
I ran out of paper.